Hi there, and welcome to the final video on the topic of graphs and transformations on chapter 4 of the AS book. So we've looked at quite a few bits on graphs and transformations. We've seen function notation. We've looked at how graphs can be translated left, right, up and down. And today we're going to be having a look at how graphs can be transformed via stretches, both parallel to the x-axis and the y-axis. Before we do that though, we have some warm-up questions for you. Here they are, 1, 2, 3 and 4. Importantly though, I want to draw attention to these two graphs which have been pre-drawn. So what are they graphs of? It does say on your notes, but I'm going to make a particular point of mentioning again that these graphs here are graphs of the function f of x, which will be explored later. F of x is x squared minus 2x minus 3, so bear this in mind throughout the warm-up. These graphs pre-drawn are of x squared minus 2x minus 3. So try these warm-up questions yourselves. If you get stuck, as ever, use a video to help you, or ask me in class if you can, and then use the video to help you understand the solutions, if you've gone wrong at all, that is. But try them yourselves first, as ever. So let's have a look together at question 1. For question 1, we need to factorise 4x squared minus 4x minus 3. Now, to do this, what we could do is use what I call the AC method. Because this coefficient of x squared isn't 1, what we can do is multiply the 4 by the constant term, which is c in terms of ax squared plus bx plus c. So we multiply these two together to arrive at minus 12. What this tells us is we need to hunt for two numbers which multiply together to give us minus 12. When we add them up, give us minus 4. With a bit of thinking, we can see that these two numbers are going to be positive 2 and negative 6. And so we can rewrite this as 4x squared plus 2x minus 6x minus 3. So we just partition this minus 4x into a plus 2 and minus 6. Now this bit will factorise, has a common factor of 2 and an x. So it becomes 2x brackets 2x plus 1. And this bit here, minus 6 and minus 3, have a common factor of negative 3. So we can factorise out that negative 3 and write 2x plus 1. And as you can see, as ever, using this AC method, we get a bracket which repeats. And so we can put this 2x minus 3 into its own bracket. And then 2x plus 1 as we had. Part B, we need to express this in completed square form, where a and b are constants. And so we can only complete the square when we've got a unitary x squared. Here we've got 4x squareds. So the first thing we do is to factorise out this 4 straight away. So factorise out the 4 from any terms involving an x. So we get 4 brackets x squared minus x, then that minus 3 on its own. Now we can complete the square on this x squared minus x part. So we take the x squared and just put inside the brackets an x. We half the coefficient of this x here, so minus 1, half that is minus a half. Do all of that squared. Then we subtract off this minus a half all squared. Minus a half multiplied together is positive a quarter. So we subtract off a quarter, and all of this is still in brackets at this point. And then minus off this 3. We can now expand this out. So we have 4 lots of x minus a half all squared. Now 4 lots of minus a quarter is minus 1. Then still got the minus 3, and as a final step we can simplify this down. So we get 4 lots of x minus a half all squared. Minus 1 minus 3 is overall minus 4. So we've got this function in two different forms, completed square form and factorised form. Put them together, we've got the roots and the turning point as well. So we can see here, if this bracket were equal to 0, x would have to be 1.5 or 3 over 2. So one root is halfway between 0 and 3, so one root is going to be 3 over 2, which is here. And the other root, 2x plus 1 needs to equal 0. That's going to happen at -1/2. And so these roots here for the original function, and just to remind you, this original function drawn in black is the graph of x squared minus 2x minus 3. So the roots have been brought in, stretched inwards by 1/2. -1 divided by 2 is -1/2. Let's think about the y-axis intercept. For this one, substitute in x is 0. 0 minus 0 minus 3. It's still going to have the same intercept at -3. The turning point, however, because this is in the form a brackets h x minus h squared minus k, these two constants tell us that the turning point is when x is 1/2 and y is -4. So the turning point is still at -4 as a y-coordinate, but the x-coordinate's been halved, so the x-coordinate is going to be about here. So now what we need to do is to plot through these points. So it's going to look like x squared minus 2x minus 3, but just squished in by factor half. So here goes nothing. It's going to come up very steeply through here. Almost vertical, in fact. And on the other side, it's going to come up very steeply past the turning point, through 0, 3, up through here, steeply, steeply, steeply. Always have that tick at the end, I don't know why. So it's going to look something like that. So it does say to label all points of intersection with the coordinate axes. That one's been labelled, that's fine. This one here, just going to make some space. That's -1/2, 0. This one here is 3 over 2, 0. And the turning point, way down here, is 1/2, 4. The half and the 4 coming from these two bits in the completed square form here. So compare the coordinates of x squared minus 2x minus 3 to the one we've just drawn in red. You can see here all corresponding x coordinates have been halved. Half -1 goes to here, half of 3 goes to here, becomes 3 over 2, and half of the x coordinate 1 becomes half. So whatever this is, wherever this comes from, it seems to be a translation of x squared minus 2x minus 3. It seems to be a stretch scale factor 1/2. So it's been stretched inwards. Each x-coordinate's been halved. Let's have a look at question 3. So first of all, it's similar to question 1, we need to factorise this. So this one has a common factor of 2 in everything. So that's 2 brackets x squared minus 2x minus 3. And just to remind you, this graph is x squared minus 2x minus 3. So this now factorises. Two numbers that multiply together to give you -3 and add up to -2. That's going to be +1 and -3. We need to write this as well in completed square form. So like I mentioned before, we must factorise out any coefficient from x squared to leave it as just 1x squared. And so first of all, we can say this is 2 lots of x squared minus 2x. We can leave that -6 on its own. Now we complete the square in these big squared brackets of x minus 1 all squared, minus off this 1 all squared, so minus off 1, all of this still in brackets at this point, minus 6. Expand out, multiply this 2 with everything on the inside, gives us 2 lots of x minus 1 squared. 2 times minus 1 is minus 2, and minus 6. So simplify that down, we get 2 lots. Whoops, what am I thinking? Can't keep up with my mouth. So 2 lots of x minus 1 all squared, minus 2 minus 6, that gives us minus 8. So in factorised form we have this, in completed square form we have this here. Now we need to sketch this accurately. So we can see here the roots are going to be where x is minus 1 and x is 3. So the roots are going to be the same as the roots here, in fact. The y-axis intercept is going to be minus 6. If you substitute in x is 0, the evaluation comes out to be minus 6. 0, minus 0, minus 6. So it's going to cross the y-axis not at minus 3, but further down here at minus 6. And as well as that, the turning point we can see from the completed square form is going to be at 1, minus 8. So this minus 4 is going to be right down here at minus 8. Okay? So now all we need to do is to draw a curve through these points, which I'm dreading because I'm awful at sketching curves, but here goes nothing. So it's going to come up steeply through there. That's pretty bad to the point where I'm almost tempted to start again, but I'll leave it for now. Okay, so that's going to come up like that, and then this side. Three minus 1, 0, up like so. Absolutely terrible sketch. Trust me, I can do it better on paper. That's my excuse. I'm going to stick to it. So let's have a look and compare these corresponding points. So the x values for each point, let's label them on. So that one, the turning point is 1, minus 8. The roots haven't changed. And the y-axis intercept, instead of being 0, minus 3, that's 0, minus 6. So the x-axis values, the x values haven't changed at all. But have a look at the y values. 0 doubled is 0 still. 0 doubled is 0. Minus 4 doubled is minus 8. And minus 3 doubled is minus 6. So the x values haven't changed. But it would seem that the graph has been stretched scale factor 2. Each y coordinate has doubled in the corresponding transformation. And so why might that be? This is what we're going to have a look at next. So bear in mind, the initial graph was x squared minus 2x minus 3. The graph I've got here is 2x squared minus 4x minus 6. So let's have a think about what's happening and why. So figure 1 and figure 2 are just essentially recapping the warm-up. So the parent function, we've got f of x equals x squared minus 2x minus 3 as a dotted curve. So let's just illustrate this a bit more clearly. So the dotted curve is this function here. So this thing here is x squared minus 2x minus 3. And the same for figure 2 as well. So what we need to do now is think about an expression for f of 2x. And so here f of x, the input is x. We want to consider what expression we'd end up with if we input not x but 2x. And so we can see from f of x, whatever the input is, gets squared. We take 2 lots of it away, then finally we subtract 3. So f of 2x is going to be 2x squared minus 2 lots of 2x minus 3. 2x all squared, square the 2, we get 4. Square the x, we get x squared, obviously. Minus 2 lots of 2x, that's minus 4x. Then minus 3. Wait a minute, isn't that exactly the same as what we had in question 1, which we plotted? It is. So what we plot on question 1, which we talked about, was actually a stretch, scale factor 1/2, parallel to the x-axis. That's one and the same thing as f of 2x. So to go from f of x to f of 2x, rather than the x-coordinates doubling, the x-coordinates are halved. Isn't that quite strange? So in words, the expression for f of 2x, like I've just said, it's the same as the expression from warm-up questions 1 and 2. When plotted, it was the same as the solid curve in figure 1. So therefore, f of 2x is a stretch of f of x parallel to the x-axis, scale factor 1/2. Now let's think about part 2. We have 2 lots of f of x. So all we're doing here is we're taking what f of x is and multiplying it by 2. So all it means is it's 2 lots of what f of x is. So it's 2 lots of x squared, just expanding the brackets here. 2 lots of minus 2x is minus 4x. 2 lots of minus 3, which is minus 6. And again, that's exactly what we were plotting in the warm-up. This is what we plotted, and we talked about in the warm-up how this here happened to be exactly a stretch scale factor 2 in the y direction. We've just shown that this is one of the same thing as 2 lots of f of x. So in other words, we can say this. So the expression for 2 lots of f of x is the same as the expression from warm-up question 3 and question 4, which we worked out. When we plotted it, it was the same as the solid curve in figure 2, which we have here. In other words, it's a stretch. So in other words, this 2 in 2f of x is a stretch of f of x parallel to the y-axis, scale factor 2. So again, like I mentioned in the last lesson, when the change happens inside the brackets, it does affect the x in the opposite way to what you might expect. So here, the x-coordinates aren't multiplied by 2, they're divided by 2, they're halved. Whereas when the change of f of x happens outside of the brackets, here this 2 is outside of the f of x, the change is a more common sense way affecting the y. So the y-coordinates do get multiplied by 2. Let's have a look at a task now. So I'm going to show you using algebra what's going on behind the scenes. So we're not just going to apply the rules and use our intuition just quite yet, although you can intuitively guess what might be going on, what g of a third of x is going to look like, but let's prove it algebraically. So we've got g of x, which is x cubed minus x squared minus 2x. Figure 3 opposite has got the graph of it in a dotted line. For part A, we need to find the points of intersection of y equals g of x with the coordinate axes and label them clearly in figure 3. So, first of all, if we want to find the intersections with the axes, your best bet is to factorize. So g of x, we can factorize it out an x straight away, and we have x squared minus x minus 2 left on the inside. Now this will factorize as well. So 2 numbers that multiply together to give us minus 2, and we add them to give us minus 1, that's going to be plus 1 and negative 2. So we can rewrite this as x brackets x plus 1 brackets x minus 2. So we can clearly see what the roots are. One root's at 0, which we've got here at the origin. Another root will be at minus 1, because minus 1 makes this bracket equal to 0. So this here has to be minus 1. and the other root must be at 2. So this one here, we can say that's 2. For part B, using the space below, find an expression for the function g of 1/3 x. So again, just consider it as an input. G of x, the input is x. We cube the input, we take away the square of the input, then we take away 2 lots of the input. Here, if the input is 1/3 of x, what we're going to do is we're going to cube the input, so 1/3 x cubed, then minus the input all squared, so minus 1/3 of x all squared, then minus 2 lots of the input. 2 times 1/3 of x is 2/3 x. So let's expand this out. So 1/3 cubed is 1 cubed, which is 1, over 3 cubed, which is 27, x cubed. Then minus 1/3 squared, 1 squared is 1, 3 squared is 9, x squared is, well, x squared, minus 2/3 x. So now we've got a bit of a mess really, but not for long. We can neaten this up. So if you have a look here, the denominators, we can factorise this. So we can see x is common in each, so we can factorise that out, but in terms of these denominators, 3, 9 and 27 all have factors of 3, and so we can actually get a common denominator in all of these of 27. So 1/9, we can think of 1/9 as being multiplying both top and bottom by 3. We can think of that as being 3/27. We can do the same for 2/3 as well. So 2/3, to go from 3 to 27, we can multiply both numerator and denominator by 9. So if we do that, 2/3, we can see that's the same as 18 over 27. So using these facts, we can go further. We can factorise out an x, and we can factorise out the common fraction 1/27. So we can say this is the same as 1/27 x. So we need to multiply this by x squared to give us this x cubed, then minus 1/9 x squared. So 1/9 is the same as 3/27. So to go from 1/27 to 3/27, we need to multiply by 3. Of course, we need this minus in because it's minus this fraction. And to go from the x to the x squared, we need an x in here. And then we need to go minus 2/3 x, which is minus 18 over 27x. So we've got the x already. We don't need to multiply by an extra x. But to go from 1/27 to 18/27, we need to multiply this by 18. And again, the minus sign is needed because it's minus 2/3 x. As a final step, we can factorise slightly further. This expression here, 2 numbers that multiply to give minus 18 and add up to minus 3, that's positive 3 and negative 6. So this factorises into x plus 3 and x minus 6. That looks quite bizarre really. So let's just have a think about what's going on, which is quite beautiful really. I don't use that term lightly. I think this is a beautiful illustration of what's going on. So look at the roots and compare. 0 and 0, so that root is still the same. For minus 1 here, we now have minus 3. Okay, so what's happening here is that minus 1 root is now at minus 3. And the root at 2 has now become a root at 6. So the 2 4 is now at 6. So it looks like the roots have been multiplied by 3. So instead of 0, minus 1, 2, we have roots now at 0, minus 3 and 6. And so why is this minus 1/27th coming into play? Well, this is the beauty of it. So if the roots are being multiplied by 3, because it's cubic, it's going to be affected by that factor cubed. 3 cubed is 27. So to correct for it not being blown up by a factor of 27 in the y direction, this 1 over 27 corrects it. So this 1 over 27 eliminates the 3 cubed factor I just mentioned, so that it's not a stretch in the y direction at all. The only stretch is in the x direction. These x coordinates, these x roots, have been multiplied by 3. And so this g of a third of x is actually just the same as this thing here, but just stretched out 3 times. Now, wouldn't it have been simpler just to have known that to begin with, rather than going through all this awkward algebra? Of course, it'd be easier just to change this and just stretch it outwards 3 times, which is what you're to do, by the way, if ever you're examined on this. But this is just a nice illustration of what's going on behind the scenes, so you're not just mindlessly thinking, oh, that's 1/3, that means stretch it by 3. Anyway, so let's crack on and do this sketch. So this little bit here is going to overlap with my sketch, so I need to just clear that off. Hope you made a note of that. If not, just rerun the video. Now we can sketch in, let's go for a blue colour, g of a third of x. So g of a third of x is this thing here. So I've put in the roots already, so that's just a case of sketching it in a blue colour. As I say, it wouldn't go any higher or lower, it can be the same height. Something like that. If only I could sketch better, you could hopefully see it's just this thing here, just stretched out like in a rolling pin or whatever it is, 3 times in both directions. So there's now an activity for you to have a go at. This is a slightly weird activity. Based on the ideas explored so far, we say, create 4 definitions for graph stretching using the keywords and phrases given in the boxes provided. Some of this information is false, and some can be used more than once, so just be careful. So a lot of these, well, some of them, don't need to be used at all. So if you can work in pairs, please do. If you're watching this alone on YouTube, obviously just do your best on your own and take me as like a virtual second person. And try your ideas perhaps on a mini whiteboard first, or just some rough paper if you don't fancy having a mini whiteboard. Once your teacher's checked your work, write your final definitions in the boxes provided. So let's just crack straight forward into the final definitions. And so the first type of transformation we could have is thinking about a graph of y equals f of a of x. So let's use this one here first of all. So this change happens on the inside of the bracket. So f of x has become f of ax. Like I've just mentioned before in the previous video too, a change from inside the brackets affects the x direction in an opposite way to what one might expect. So rather than the coordinates of x being multiplied by a, they get divided by a. So it's a stretch of y equals f of x, it's the first thing to mention. And it's going to be scale factor 1 over a. Rather than multiplying by a, we're going to be dividing by a, which is the same as saying timesing by 1 over a. Let's get this in a line. There we go. As well as that, we need to say which direction it is. It's in the x direction. And as well as that, we can't divide by 0. Okay, so it's a stretch of 1 over a, where a can't be 0. So we need that little caveat in as well. The next one we can consider is the graph of y equals f of 1 over a of x. Okay, again, the changes from inside the brackets, so it will affect the x direction. So again, we can say it's a stretch of the graph y equals f of x, so we can use this one here all the time really. Like we saw in the previous example, we had g of a third of x, that stretched it out a factor of 3 times. And so this stretch here, this number, always stretches scale factor of the reciprocal of itself. So if it was an a, it stretches scale factor 1 over a. If it's 1 over a, the stretch is going to be scale factor 1 over a, which is actually going to be a. So this scale factor here is going to be a. In the example we saw earlier, it was 1/3, that stretched it by factor 3. Again, like I say, it's in the x direction, and a can't be 0. You can't divide by 0 unless you want the universe to explode. I don't want it to, and I'm hoping neither do you. The next type to consider is where the change happens on the outside of the brackets. So for example, we could consider now y equals a f of x. This one here. So the graph of a f of x, again, it's a stretch of y equals f of x, so we can use this card again. It's outside the brackets, so it works in a common sense way. So this is multiplying f of x by a, so it is by scale factor a. So we can use by scale factor of a again. This time it's in the y direction because this a is outside of these brackets. And so we need to say in the y direction. And the scale factor is just a itself. And the last one, there's one more because there's 4 definitions we need, is the graph of 1 over a f of x, this one here. So the graph of 1 over a f of x, again it's a stretch of y equals f of x. Because this is outside of the brackets, again it's going to be affecting the y direction, and it's in a common sense way. So it's going to multiply f of x by 1 over a. In other words, the scale factor is 1 over a, and it's in the y direction. More than that, because we've got 1 over something, we can't divide by 0. So again, we must stipulate where a is 0. Just notice this one, I've put scale factor of a twice. I don't need to put it twice. There we go. That's what I mean to put. So let's just summarise now. So there's the 4 points in summary. Looks a bit technical, lots of algebraic expressions there. Let's try and get it into plainer English if we can. This still holds, I'm not saying forget this, I'm just saying let's try and interpret it in plain English where possible. So, some useful interpretations we can apply. I've mentioned this before, I'll mention it again. If f of x changes from f of x to something where inside the brackets looks different, so for example f of 2x or f of a third x or f of x plus 2, that affects x in an opposite to expected way. So for example, f of x going to f of x plus 2, we minus 2 from the x coordinates. If, however, it's a change of f of x which occurs outside of the brackets, that affects y, not x. And that effect is in a very common sense way. So, to put this into the summary of what we're dealing with here in terms of stretches, if y of f of x is translated to y equals f of ax, rather than multiplying the x coordinates, that a actually has the effect of dividing all x coordinates by factor a. On the other hand, if we have y of f of x being translated to y equals a f of x, that multiplies, as it looks like it's doing, as I say, the common sense way of thinking about it, that does multiply the y coordinates, because it's outside of this bracket here, by this factor a. And so that's a more colloquial, yet perhaps more useful way of thinking about things. So if you'd like to, feel free to make a note on that. Let's try some examples now. So one example, sketching graphs of stretched parent functions. So in this case, parent just means for the initial function we can adapt. So our parent function is f of x equals x cubed minus x squared minus 12x. And we have these different stretches to try and work out. So first of all, what we need is 3 sets of axes, like so. So first of all, we need to sketch f of x itself. To do this, best thing I can suggest doing is to try to factorize this here. So if we were to factorize, we can factorize out an x, and inside the brackets we're left with x squared minus x minus 12. Now inside the brackets that will factorize again. Two numbers that multiply together to give negative 12 and add up to minus 1. That's going to be x plus 3, x minus 4, because 3 times minus 4 gives minus 12, and 3 take 4 gives us negative 1. So it's a cubic, x is a common factor, so it's going to go through 0. This x cubed is positive, so it's going to have a shape like this. So we've got what we need to sketch it now. So one root's going to be at minus 3. The other one's going to be a bit further over at 4. And we're going to have something looking a bit like this. Down. And back up. Now, we've done this. We don't need to bother algebraically with any more manipulation. We can use what we've talked about previously to work out what f of half of x would look like. This change here, the x has changed to half of x, so it's the inside of the brackets which has changed. Because it's the inside of the brackets, it affects x in an obvious common sense way. So common sense, you might think, well, these x coordinates are going to be halved. Opposite to that, the x coordinates are going to double. And so what this is going to do, the x coordinates are going to double. So for part B, that's a stretch, scale factor 2, in x direction. So let's have a go at doing that. So what I can do here, a luxury you don't have, is I can pretty much cheat. Because it's going to be a stretch, scale factor 2 in the x direction. I can take this curve here, which we've already done, and just stretch it so it's double as long. So what I'm going to do here, I'm going to take this, stretch it out, so it looks something a bit like this. Now, I'm not saying it looks perfect, but I've done it that way just so you can literally see what's happening. It's literally a stretch. You don't have to replot. It's just a stretch like any other. And so what I'm going to do here, I'm going to save that one there. I'm going to pop the original back in its place. And I'm going to paste in this into its new place. And so, as I've said, this one here, stretch scale factor 2 in the x direction, and so each x coordinate doubles, so minus 3 will become minus 6, and this 4 will double to become 8. Next, for part C, we need to consider what y equals half f of x will do. So we're going from y equals f of x to y being half f of x. Because a half is outside of the brackets, this will affect the y coordinates in a common sense way. Each y coordinate will be halved. It's going to be a stretch scale factor a half in the y direction. So the x coordinates won't be affected. The roots will still be the same. We'll still have roots of minus 3 and 4, but what we will have is a shrinking, if you like, of this graph in the y direction. It won't look quite so elongated in the y direction. So what I'm going to do here is just shrink this down and pop it in here. and then just maybe tinker with the edges, just for completeness. Almost wish I hadn't now, that looks totally wrong, but never mind. So -3 and 4 are still in the same place, but as you can see, these humps aren't quite as big. They're only half the size because the y-coordinates of these maximums and minimums have been halved. But the x-coordinates are invariant, they don't change. So the roots are still -3, 0 and 4. Let's now have a look at another example. So here, we've got g of x, which equals x squared minus 2 of x, and that's already begging to be factorised. And so we can rewrite this as x brackets x minus 2. Okay, so even if the question doesn't ask us to sketch g of x, that's what I'm going to do now. So I'm going to sketch g of x on a coordinate grid. So let's just pop in here the axes. So y and x, and we can plot this one fairly easily because it has roots at 0 and 2 and a y-axis intercept of 0. It's going to go through the origin. So if that's the x-coordinates, so the x-axis and this is the y-axis, this one here is going to have roots at 0 and 2. So I'll just put 2 here. And it's going to look something a little bit like this. Okay, so that's g of x. Now for a, we need to consider what g of minus x will look like. Well, g of minus x we can think about as g minus 1 multiplied by x. Okay, this change is inside the brackets and always works opposite to what common sense might dictate. So the x coordinates aren't going to be multiplied by -1, they're going to be divided by -1, which actually, because it's -1, that's the same thing. So this coordinate here, which is at 2, that's going to be multiplied by -1, and that 2, therefore, for g of x, will become -2. 2 multiplied by -1 becomes -2. This point here, multiplied by -1, it's a negative. When we multiply it by -1, it becomes positive. This x-coordinate here will map over to this x-coordinate here, and so on. This minimum, which is halfway between 0 and 2, that minimum's at 1, that gets multiplied by -1. 1 times -1 is -1. So actually what happens is this. So this bit ends up being mapped over here, like so. That's a root at -2. 0 times -1, or 0 divided by -1 is still 0, so that is invariant, that bit doesn't move. Then it comes up because it's still a positive shaped parabola, still a U shape. And so because each x-coordinate is multiplied by -1, the x-coordinates mirror in the y-axis. That's to say that g of minus x is a reflection of the function gx in the y-axis. That's a general result. And so in blue, I've drew in g of minus x. Now b, for b we have minus g of x, which I want you to think about as being -1 multiplied by g of x. So the brackets are still the same, still has an x. This change from g of x to minus g of x, the change happens outside of the brackets. G of x is being multiplied by -1, so the y values only are affected, the y values are multiplied by -1. So where y is positive, it becomes negative. Where y is negative, it becomes positive. So what that is saying is that minus g of x is a reflection of g of x in the x-axis. That too is a general result. So minus g of x, that's a reflection of g of x that's a reflection in the x-axis. And these are general results. So normally it'd be f of minus x and f of x, or minus f of x, but whether it be f, g, h, whatever, the general rule is the same. Minus f of x reflects f of x in the x-axis. F of minus x would reflect f of x in the y-axis. So all we need to do now is to sketch minus g of x. It's a reflection of this black curve g of x in the x-axis, and so this bit here gets mapped as such, and then going down accordingly. And the same on the other side. So this here is minus g of x. Lastly, a worked example where we don't know what function we're dealing with to begin with. So I've called this an unfamiliar function. So we have a sketch of a curve y equals h of x, which passes through the origin here. The point A at 1, 4 and B at 3, 1 are also on the curve. We need to sketch the following A, B and C in the boxes provided, indicating the positions of where the translated points 0, A and B end up. So the first one, we need to sketch h of 2x. So again, if you look here, this change is inside these brackets. So what's going to happen here is that this is going to be a stretch parallel to the x-axis, but the x-coordinates aren't going to be multiplied by 2, they're going to be divided by 2. So it's a stretch scale factor a half. The x-coordinates are going to be halved. Stretch scale factor of a half along the x-axis. Okay, so what we're going to do here is take this graph. I'm going to cheat in a sense. I'm going to take this, okay, and it was like this. That's where it was. But what we're going to do now is we're going to imagine this being shrunk inwards. We're going to imagine this being shrunk into something looking a bit like this. Okay? So that's where it ends up. So I've done it like that instead of redrawing it, so you can literally see the shrinking effect. So the point O, which goes through the origin, the x-coordinate of that gets halved. So because it's 0 anyway, 0 divided by 2, that still stays at the origin. So that's still 0, 0. For point 1, 4, the 1 gets halved, so this point here becomes 1/2, comma 4. And this minimum, the 3 gets halved, 3 divided by 2, we can just leave as 3/2 and comma 1. For part B, we have half y equals h of x. We need to multiply both sides by 2 to arrive at y equals 2h of x. So it's h of x multiplied by 2. So it's going to be a stretch, scale factor 2, but this time, because this 2 is outside of the brackets, it's going to be affecting the y direction. So it's a stretch, scale factor 2, along the y-axis. In the same way as I cheated earlier, I'm going to cheat now. I'm going to just nick this curve here and imagine it being stretched. So initially, we have h of x like this. If I imagine this being stretched, okay, I'm going to keep it roughly the same width and stretch it double. It's going to look something a bit like this. Okay, I know it goes off the page, well, off this box, but never mind. At least you see the result. Now, because it's a sketch, I didn't need to do it in exact scale. I could have just labelled these points, so don't think you have to do it exactly as I'm doing it. I'm just trying to illustrate what's going on. In fact, what I'm going to do now, I'm going to get rid of these boxes just so you can see clearly what's going on. Whoops, didn't mean to do that. Or that. In fact, I think I'll just leave this on. So I need to just label these points on, don't I? So this point here, okay, it's 0, 0. So when I multiply that by 2, that's still going to be the origin. That's still 0, 0. This point here, the y-coordinate will double. So the 4 will double to 8. 1 will stay as it is. So we have 1, 8. And this one here, that's going to be 3 and 2. Now for the last one, C, we have minus y equals h of x. So I'm just going to give myself a bit more space for C. If I multiply both sides by minus 1, I'd see that y is going to equal minus h of x. So the change is outside of the brackets. It's going to affect the y-axis. It's going to affect the y-coordinates. Think of this as being minus 1 multiplied by h of x. So this is going to be a reflection in the x-axis. If you're thinking, as you might be thinking, what if this were minus 2 or minus 3? You can have a reflection and a stretch. So for example, if this was say minus 4 h of x, you can think of this as minus h of x first, reflect it, and then stretch it scale factor 4 afterwards. So you can have a stretch and a reflection at the same time going off. So anyway, because this is a reflection, I'm just going to give myself a bit more space, which I failed to do with this one because I was getting it all muddled up. But here, I've managed to sort this one out. Okay, so what I'm going to do here, I'm going to get the curve, and now I'm going to ask for it to be flipped up and down, literally reflect it, and this shape here, the 0, 0 point, will still be at 0, 0, by the way. It's still going to go through the origin. And we'd have something looking a bit like this. And so where we had 1, 4, that 4 is going to be multiplied by minus 1. The y values get multiplied by this minus 1. The x values don't. So A is going to be mapped to 1 minus 4. And the coordinate that was B we had 3, 1. That's now going to be 3, minus 1. Because a 1 is multiplied by negative 1. And as ever, this origin point doesn't change. That's invariant. So that just stays anchored at 0, 0 in these cases. And that's all there is from me on this topic for today. So now it's over to you guys. If you could try these exercises, so first of all, page 78, exercise 4F, just these questions in particular, and then move on to exercise 4G, questions 1, these parts, question 2, these parts, then 3, 4, 5 and 6 in order. As ever, if you get stuck, ask me, and use the book regularly to self-assess. Don't do loads of questions, then only check once at the end. Do a question, check it. Do and check regularly. So keep working hard, keep trying your best, and you'll see me, I hope, soon. Take care, and thanks for listening.